Welcome to this session on drilling optimization, well-designed process to execution. This is sub-module 2 of 4 in the drilling optimization series. In this module, we'll explore how forecasts are built, applied, and reviewed throughout the drilling process, setting the stage for evaluating and improving overall performance. In this session, we will focus on 5 key learning objectives. First, we will understand the role of forecasts in drilling performance planning and how they provide the foundation for safer and more efficient operations. Second, we'll identify the main components that make up a comprehensive drilling forecast, including time breakdowns, risk assessments, and contingency planning. Third, we'll examine how modelling tools are used, while also highlighting the limitations that come with depending on simulations and software. Fourth, we'll see how real-time data is integrated into the forecast to manage change as operations progress, ensuring that plans remain dynamic rather than static. Finally, we'll review how drilling performance is evaluated by comparing forecast expectations with actual field results. These objectives will guide us step by step through the sub-module and provide a structure for what follows. Forecasting in drilling is not a one-time task. It is a continuous process that guides us through the entire well delivery cycle. We begin by designing the forecast, which establishes expected performance, risk awareness, and operational parameters. From there, the program undergoes review to ensure assumptions remain valid before execution. As the well is drilled, control and monitoring are applied in real time. This ensures that the execution phase is guided by accurate and up-to-date information, not just the initial design. Once execution is underway, reporting becomes critical. The performance of each stage is documented, highlighting variances between the plan and the actual results. Finally, this information feeds into continuous review, closing the loop. Lessons learned are captured, risks are reassessed, and plans are revised for future wells. This cyclical approach ensures drilling efficiency, safety, and knowledge growth. In short, forecasts provide the framework for design, control, and execution, but it is the continuous review that ensures they remain relevant. With that foundation in mind, let's move on to see how forecasts are used to assess performance and revise plans. Forecasting also plays a central role in assessing performance and revising plans as conditions evolve. At the planning stage, forecasts are built using offset well data. This allows us to anticipate potential hazards, identify best practices, and clearly define methods for detecting early warning signs. As drilling begins, the forecast is translated from a risk register and daily updates. Real-time engineering data feeds into this process, ensuring risks are continuously re-evaluated. Key drilling parameters such as pressure, torque, and rate of penetration are monitored closely to confirm that actual values align with predicted outcomes. When deviations appear, the forecast is updated with new information. Hazards are reforecasted, mitigation measures are applied, and performance is tracked by comparing actual results against the plan. If the comparison shows alignment, drilling continues as expected. If not, the process requires diagnosis and corrective action before proceeding. The final step is evaluation. Here, knowledge is captured, differences between plan and reality are documented, and revised methods are fed back into future designs. This feedback loop builds a stronger, more reliable forecasting process. Having understood this performance cycle, our next slide introduces a short video demonstration using petrol mechanics to illustrate how forecasts integrate into the design workflow.
We understand that predicting changes in stress in the subsurface throughout the E&P lifecycle is fundamental to the performance of your asset. There are some big questions you need to answer. How can I understand the risks associated with drilling my first well? What type of well should I drill? What is the best completion? Will my casing withstand changes in pressure? What is the highest injection pressure? Knowing how stress is distributed in your reservoir enables you to answer these questions. Schlumberger software solves today's complex subsurface challenges by providing critical insights into the mechanical behavior of your asset and the surrounding rock. so you know where to place your wells and how to design the best field development plan. See how the health of your reservoir is changing over time. Determine the optimal depletion and injection pressures that will keep the reservoir seal intact. Understand if your faults will withstand the changes in pressure you are planning. And anticipate compaction issues before they happen. Schlumberger geomechanics software puts all these capabilities at your fingertips. Designed to integrate seamlessly into the E&P workflow of asset teams, our industry-leading software gives you the knowledge and insights required to find the right answers to the big questions, so you can proactively control risk in the most effective way and optimize the value of your asset throughout the life of your field.
A robust drilling forecast must be more than a schedule. It is a comprehensive plan that captures both expected performance and potential risks. The first component is a detailed time breakdown, which maps out each stage of operations and provides the basis for monitoring key performance indicators. These KPIs allow us to measure progress and flag variances early. Next, the forecast includes a thorough risk analysis. This covers decision points where the operation may need to adjust course, mitigation measures that outline how to respond to identified risks, and contingency points that ensure backup options are always available. Drilling models form the backbone of the forecast. Torque and drag, hydraulics, mechanical earth models, and time and cost simulations all provide predictive insights. Geological models are equally critical. They describe structural features such as salt domes and help anticipate stability challenges or reservoir entry conditions. On the right-hand side of the slide, you'll see images of a geological model and a fishing decision tree. The geological model illustrates how subsurface features can affect drilling paths, while the decision tree shows how structured workflows guide operational choices when unexpected events occur. Together, these elements ensure that forecasts are not just predictions, but actionable plans. Responsibility for the drilling forecast ultimately lies with the drilling engineer. This role involves integrating offset data, risk assessments, modeling outputs, and operational planning into a single coherent forecast. However, it is important to emphasize that the forecast is not a one-person task. Risk analysis and well design are inherently multidisciplinary. Geologists contribute by defining formation properties and structural risks. Petrophysicists add insight into pore pressures and fluid contacts. Drilling engineers model torque, drag, and hydraulics. HSE specialists address operational risks. Together, this collective expertise ensures that the forecast reflects all aspects of the well. Because so many disciplines contribute, communication and teamwork are essential. A forecast loses its value if knowledge is siloed or assumptions are not shared. That is why collaboration and transparent reporting are built into the process from the beginning. In short, while the drilling engineer is accountable, the forecast is the product of a team effort. This multidisciplinary approach is what gives the forecast its depth and reliability. On the next slide, we'll look at how this forecast is actually presented within the well program. A drilling forecast is not a standalone document. It must be presented as part of the well program. By integrating directly into the program, the forecast becomes a working tool rather than an isolated report. It should fit seamlessly into the design process, ensuring every engineer and manager has the same reference point. Forecasts are often communicated through graphical summaries. These are usually large format plots displayed in planning offices or on the rig. The intention is to provide a clear, at-a-glance view of the expected drilling process, highlighting key risks, performance benchmarks, and contingency points. In the field, this graphical summary is often referred to as the driller's roadmap. It is used to guide day-to-day operations, providing a quick visual check against planned progress and helping crews anticipate upcoming risks. This method of presentation ensures that forecasts are not just theoretical. They are practical tools that crews and engineers can use directly. Next, we will explore an example of such a driller's roadmap in more detail. Here we see an example of a driller's roadmap which illustrates how forecast data is turned into a usable operational guide. At the top, the stratigraphy is displayed, showing the expected geological layers that the well will encounter. This immediately alerts the driller to transitions between formations that may present challenges. Below, a mechanical earth model is overlaid. This model highlights geomechanical risks, such as zones with high stress or weak formations. By linking stratigraphy and earth model data, the roadmap provides both geological and mechanical context for drilling decisions. On the right-hand side, we see a graphical presentation of risks, alongside descriptive notes and advice. These annotations explain the nature of potential hazards, for example, differential sticking or lost circulation, and outline how they should be mitigated. The purpose of this roadmap is twofold. First, it provides the driller with situational awareness in real time. Second, it acts as a communication tool between the office and the rig, ensuring both parties are aligned on expectations and contingency measures. By converting forecast data into a clear graphical roadmap, we transform complex planning into a practical guide. With this example in mind, we can now move on to examine how forecasts rely on modelling expected performance. Modelling expected performance is a critical part of the forecasting process and an integral part of well design. A forecast is only as strong as the models behind it, and these models allow us to test scenarios before the bit even turns to the right. Key modelling areas include torque and drag, which help us understand the mechanical loads acting on the drill string. Hydraulics modelling ensures that mud circulation is effective for hole cleaning and pressure control. Mechanical earth models predict rock strength and stress, guiding casing design and wellbore stability. Production models allow us to forecast well deliverability once drilling is complete, linking the drilling plan to long-term reservoir performance. Risk models identify potential hazards and quantify their likelihood and impact. Finally, time and cost models set realistic benchmarks for budgeting and scheduling. Together, these models provide a comprehensive picture of expected drilling performance. They allow engineers to anticipate challenges, balance risks against costs, and design wells that are both safe and efficient. However, it's important to remember that all models come with limitations. They are representations, not exact replications of reality. To properly understand modelling, we must first define what a model actually is. A model is simply a representation of something. It may be a physical object, such as a scaled-down version of a rig or formation, or it may be a mathematical or descriptive framework used for calculations. This definition also highlights the fundamental limitation of all models. By their very nature, they are simplifications. They cannot capture every variable, nor can they replicate the complexity of the real world. Instead, they focus on the most significant factors to make problems manageable and to provide useful guidance. For example, a torque and drag model assumes certain friction factors that may change downhole. A hydraulics model simplifies fluid rheology to predict pressure losses. While these are essential tools, they are not exact predictions. Understanding these limitations is crucial. Engineers must use models as guides, not guarantees, and be prepared to adapt when actual conditions differ. This brings us naturally to the next topic, the additional limitations imposed by computerized modeling and the software tools we use every day. Computerized modeling is the standard in drilling today, but it introduces its own set of limitations. Software programs are powerful, but they are only as good as the inputs provided and the assumptions built into their algorithms. A common saying is, garbage in, garbage out. If the input data is poor, whether it's incomplete offset data, incorrect fluid properties, or misinterpreted formation pressures, the software will still generate results, but those results will be misleading. Furthermore, software packages often rely on default parameters or simplified assumptions. For example, fluid models may assume constant rheology, or torque and drag calculations may fix friction factors. These assumptions can mask real variability in the wellbore. Another limitation is user overconfidence. Engineers may assume the software output is definitive, when in reality it is just one possible representation. Critical thinking is always required to validate and challenge the results. In short, computerized modeling is invaluable, but it must be applied carefully. The engineer's role is to understand the limitations, verify inputs, and interpret outputs with judgment. Next, we'll look at how modeling is applied during execution through workflows that integrate forecasts with real-time data. Modeling is not just a design phase tool, it is actively applied during execution. The core principle is to compare expected measurements from the model with actual downhole measurements in real time. When a deviation from plan is observed, the workflow begins with investigation. The engineer asks, why is this different? Is the deviation due to unexpected geology, incorrect input data, or changing downhole conditions? Once the cause is understood, mitigation measures are put in place. This could involve adjusting mud weights, modifying drilling parameters, or deploying contingency equipment. At the same time, the forecast model is updated to reflect the new conditions. This process is closely tied to management of change. Any adjustment to the plan must be communicated, documented, and approved to ensure operational integrity. The key models most frequently applied in execution include torque and drag, hydraulics, mechanical earth models, and risk frameworks. Time and cost models are also updated continuously to track progress against plan. By embedding modeling into execution, the forecast becomes a living tool rather than a static plan. Next, we will review our objectives to close this submodule. Let's take a moment to review the objectives we set at the start of this submodule and reflect on how we have addressed each one. First, we set out to understand the role of forecasts in drilling performance planning. We saw how forecasts provide the foundation for design, execution, and continuous review, guiding every stage of the well delivery process. Second, we aim to recognize the key components of a comprehensive drilling forecast. We walked through detailed time breakdowns, KPIs, risk analysis, contingency planning, and the integration of drilling and geological models. Third, we discussed modeling applications and their inherent limitations. We defined what a model is, examined its simplifications, and highlighted the risks of relying too heavily on computerized outputs without critical oversight. Fourth, we learned how real-time data updates forecasts and enables proactive management of change. By comparing expected performance to actuals, engineers can quickly identify deviations and take corrective action. Finally, we covered how drilling performance is evaluated by comparing actual results with forecasts, capturing lessons learned, and feeding them back into future plans. Together, these objectives reinforce the importance of forecasting as both a planning and a learning tool. With these objectives reviewed, we're now ready to close the submodule. This concludes submodule 2 of 4 on well-designed process to execution. You've now seen how forecasts are built, applied, and refined during drilling. Please proceed to the quiz to check your understanding of the material we've covered. Thank you for your attention, and I look forward to the next session.